Okay, so we should start. Hi everyone, and thanks for joining the ROS2 Embedded Working Group today. Welcome to the first meeting of the year. We have a very interesting agenda today. And for those who are joining for the first time, my name is Maria Merlan. I work in Proxima with Pablo Garrido, the technical manager of micro-ROS. And together we are hosting this working group on a monthly basis. The document I'm sharing gathers the detailed agenda for today. So I would recommend you please to add your names to the attendee list in the document that I'm sharing. Share it also in the chat. Okay, so today, as you have seen in the agenda, we invited a couple of speakers. First, we will have a presentation by Benjamin Cabé, the Principal Program Manager at Microsoft Azure IoT, about micro-ROS and Azure RTOS. After that, we are having Dominik Nowak, CEO at Husarion and CTO at Husarnet, and he will actually be presenting two different topics: the P2P access to ESP32 ROS to nodes with micro-ROS and Husarnet VPN. And after that, he will be talking about this robotic platform, ROSbot XL, which is a micro-ROS-based autonomous platform for research and quick prototyping. And after that, Pablo will be presenting briefly a summary of the latest enhancements of micro-ROS, like CAN-FD or other important contributions from the community, as well as the Capra launch that happened last week. And I kindly invite you to, if you want to treat any different topic, you can add them into the miscellaneous section of this document, and it will be discussed at the end of the meeting. So, well, I want to thank the speakers, Dominik and Benjamin, in advance. And I want you all to know that there will be some time for questions and answers at the end of the presentations. So we can start with the first talk. Benjamin, would you please share your screen?
Yes. Ready?
Thank you.
All right. Yeah, thanks for the intro. Thanks. I'm actually pretty excited. This is my first working group meeting, hopefully the first of many. Yeah, I want to share. This is a very demo heavy talk today. I want to show a few things that can be done when you start combining micro-ROS with an RTOS, namely the Azure RTOS ThreadX real-time operating system. And maybe more importantly, what happens when, although we are talking super small devices, super constrained, what happens when you start thinking about them as devices that may be connected to the internet and to IoT platforms? What does that enable in terms of robotics use cases, like predictive maintenance and all things simulation, etc., etc. So yeah, I will try and make sure that I don't go over time too. There's that, but we can always chat more offline too. Yeah, as a way to maybe kick off the discussion, this won't be news for many of you, I'm guessing, but obviously, and especially like it doesn't have to be in the micro-ROS context, even in a good old ROS context. Obviously, robotic systems are very much distributed, right? In many many different components, software components, even if you will, that may be involved in controlling the robot. But it's even more than that. It can also be distributed like geographically. And if we're talking shop floor, there might be different components of the same system that are spread across different so-called nodes, right? And that distributed access aspect goes hand in hand with the fact that you want things to be real time, right? And real time on constrained devices, sometimes it might actually make sense to have support from the hardware itself and or from an operating system that helps you make sure that whenever the robot arm detects that there is a human in proximity, then like robot arm actually needs to stop right away, right? And it needs to be, it's actually sometimes really, really critical to do that. And we are also talking more and more about connected use cases, right? Connected as in, I guess, locally, like to implement the distributed aspect of the robotic system. You may need and rely on this connectivity aspect, but it's also about making sure that the whatever data the robots are manipulating, making sure that this data at some point makes it to the IT environment, right? And I mentioned before predictive maintenance. It actually makes a lot of sense to start collecting the data and the metrics that you may get from a servo motor or from like any other sensor or actuator, really, and store this data potentially in like large time series database and use the data to do predictive maintenance kind of stuff, right? And what is the kind of support we can get from the silicon, from the operating system, and more to help implement such scenarios? I guess this is what I want to cover today. So I'm sure this has been mentioned one way or the other before, and or many of you might not have even need this kind of refresher. But when I, at least, talk about an RTOS, a real-time operating system, I'm really thinking like a really thin layer that you add on top of the silicon, so that to help run software in a way where you have potentially multiple tasks that work hand in hand, and the operating system is there to make sure that the processing time is allocated properly, and the priority of the different tasks is enforced. And we're thinking small, as in like small MCUs, not even a megabyte of flash, and potentially a few hundred Ks of RAM, maybe even less. Not necessarily any form of a graphical user interface. And yeah, that's what a real-time operating system is. And it turns out that I'm Benjamin, by the way. We did the intro, but I work at Microsoft, and Microsoft acquired a few years back a company by the name of Express Logic, which happens to ship and to build a real-time operating system, which is actually pretty pervasive and pretty well adopted. There's actually billions of devices out there today that run Azure RTOS and the sort of the galaxy of middleware that's available in the Azure RTOS ecosystem. But yeah, you name it, like from phones to printers to IoT gadgets, IoT devices, satellites, and so on and so forth. This is a pretty popular operating system out there. My point today, actually, although I'm from Microsoft and from the Azure group, is not necessarily to pitch Azure RTOS, like to do the commercial pitch, is more to talk about, like, in general, what is the why it makes sense, in my opinion, as a community for the ROS and the embedded ROS community to start looking at IoT scenarios. And turns out that Azure RTOS is sort of the first step towards making it really easy to implement IoT scenarios on top of micro-ROS. So yeah, Azure RTOS, like historically, I guess, would be what's called ThreadX, right? ThreadX being the actual operating system, providing the all the functionality to run multiple tasks and to make sure that there is good hardware abstraction, memory management, memory pools, and you name it. But then there's a whole galaxy of supporting libraries around it that actually make a lot of sense. I mean, some might be super specific to some applications, right? Like the FileX or USBX stack to implement a file system or to implement a USB communication stack. But in the context of robotics and IoT, there is a full-blown networking stack with UDP, IP, TCP, IP support, TLS for security, and more actually, which is pretty convenient because that means that this can be used to actually power the micro-ROS local UDP-based networking stack. But this also means that if the MCU allows us to afford it, we can potentially also implement scenarios where we use TCP/IP to actually reach the internet, right, and to send data potentially to public clouds, or at least to beyond just the ROS and micro-ROS local namespace, right? And there's also a GUI stack called GUIX, which is also something that I think can become pretty relevant in a ROS and micro-ROS context, with just a very small overhead. You can start thinking about adding an actual user interface to an MCU-based node, right? And you start displaying the incoming telemetry. You start implementing a user interface where you have maybe a touch screen that allows to change some parameters in the system, things like that, right? So that's that was the sort of the intro to Azure RTOS. And between the lines, when I mentioned the networking stack, I sort of implied the fact that the networking stack is going to be what's going to enable the micro-ROS UDP-based communication between the different nodes, and between the nodes and the agent and things like that. But it's also what allows us potentially to connect to an IoT cloud platform such as Azure IoT. So the demo today is looking at I guess sort of the 101, it's almost robotics 101. We're going to control a robot arm, but we want to, control the arm, but we want to do it also potentially remotely. And we wanted to sort of take part in a more complete sort of smart factory scenario. So the first part to the demo is just a quick intro to what are the different pieces that are there, and we're just going to build the basic robot. This is pretty much, I guess, Pablo's original demo that he built a few months back to showcase how a robot can be controlled using an STM Cortex M4 based MCU that's running Azure RTOS ThreadX, NetX Duo being the networking stack, so that we have UDP/IP support on the device, and then it's Wi-Fi based for the actual transport, and then we have the micro-ROS client, obviously, and then a ROS node running on my desktop computer, my desktop PC, was going to be a joystick node publishing commands regularly to the ROS2 data space, and then by means of the micro-ROS agent, we expose this topic to the rest of the world, or to the rest of the micro-ROS world, and that's what the robot accesses when it's interested in getting some information regarding what should be the position of the arm. And that's the first part to the demo. So if I'm I guess I should, let's see. I'm gonna just stop presenting so that I go back full screen. And so that's the robot right there. And if I just open up my my joystick application, I can control the robot behind me, right? and hopefully I won't do something stupid and like crash it somewhere in the on the floor. But that's the basics, right? Like it's cool, it's fun, but it shouldn't be that impressive to you folks. It's still the micro-ROS sort of basics. Then comes the part where I want to do stuff more remotely. And then for that part, there's actually not much that I had to change or to add to the to what Pablo had built originally. Essentially, Azure RTOS ThreadX was already there. NetX Duo was already there. The only library, if you will, that needed to be added was the Azure IoT client, because the idea there is really to be like, okay, how about we not only have this UDP socket open, talking to the micro-ROS agent, so that locally we can get some informations regarding what is the subscribe to some topics, publish to some topics, and do some like pure ROS stuff. But then, thanks to the Azure IoT library, the idea is that for whatever data we consider makes sense to be reported to the IT environment, then we do it, right? We use the Azure IoT SDK to be like, hey, you know what? Every 5 seconds, I'd be very much interested in reporting to the server what is the position of the servo motor, or I want to report the battery level of the device, or the available amount of memory that's left, because this might help maybe trigger some alerts in the backend to like, we want to send a technician and we want to remotely be able to do so. We don't like the technician won't even be looking at the device locally. It will just receive a notification when something happens on their on a device they are responsible for, right? And so if I switch to the Azure IoT Cloud backend, the idea here, what I want to show you essentially is what happens when you start connecting the device to the IoT platform, right? And so this is Azure IoT Central. And in a nutshell, without diving into much details here, it's providing us with a dashboard to monitor not only one robot, but potentially a fleet of thousands of robots, right, that all send at regular intervals, send data, right? And so right now, my robot is DovBot 001. Last time it communicated is at 19 past 5, which is, a few minutes ago. It's the last time that it had something meaningful to report, which makes sense, right? It's the last time I updated its position, but now it's not doing reporting new stuff. But we can see the last thing that it reported is the position of the different servos. One thing that I can do is potentially send a command, right? I can remotely, without any direct human intervention on the robot locally, over the internet, I can be like, hey, you know what? There is a human, like a maintenance operation that's planned. Let's disable the servo motors altogether. And I think you can all see my webcam still, although this time it might be small, but you can see that I can actually move the robot by hand now, which I can't if I now it's stuck, right? So I sent the command. Hopefully you actually saw that it was pretty fast as well. And I have essentially a user interface, a dashboard, a single pane of glass to control all my devices, right? I can easily build dashboards where I have really nice overview of what's going on in the field. And beyond that, from Azure IoT Central, where the I guess the view here is very device centric, right? It's sort of like it's almost like what so-called device management, right? I can see what the device is doing. I can see that it's connected. I can see that it's sending data. I'm sending commands, but this doesn't tell me much about the whole context, right? this is a robot arm after all, right? And it's part of a shop floor. It might be a robot arm operating a particular conveyor belt. And from 4 to 6 in the afternoon, that conveyor belt is manufacturing a specific part, right? And maybe in 2 hours time, it will be another part that's being manufactured. And all that information is part of a larger system, right? It's part of my enterprise system. And I have some bits in SAP, some bits in wherever. But this is where we start wanting to tap into, I guess, the so-called metaverse, right? This is this sounds very much like a buzzword, but it's very real. It's this idea of, and you may hear it being referred to as digital twins too, right? This idea of what is the like this physical device, this physical robot arm. What is its digital counterpart in the enterprise system? So right here, this would be this guy over here, right? And all the data that it's reporting, it's there too, but there's also more context to it, because there might be other entities in the system. There are workers, there are factories, assembly lines, conveyor belts, schedules from the workers, all the kind of data that you might be interested in querying to do your business, right? You want to find someone is calling in sick on a particular assembly line. You need to find someone who was trained, was the proper training to replace them, right? And you want to do these kind of queries. Similarly, the robot arm starts failing on a particular conveyor belt. Is there a way to repurpose another conveyor belt and have it do the run the same process kind of stuff? So this idea of modeling your complete the knowledge graph of what is the relationship between the different entities of your system is something that can be modeled using a digital twins platform, such as Azure Digital Twins in that case. And once you have that information modeled, it can be exposed obviously through APIs. And that part of the demo now is showing you what you can do when you start querying the digital twins graph through APIs. And actually, before I do just that, I will make sure that I disable the torque again of the device, because it might prove useful for the remainder of the demo. This is Blender. Blender is an open source 3D software. It's not necessarily very specific to CAD and like actual industrial design, but it's open source and it has a really nice API. So I thought it was a good way to showcase how easy it is to use any sort of software really, and feed data that you get from the digital twins graph into the software. And in my case, the what I've modeled, the model I have is the model of my entire factory, right? And I might be like designing the new version of my factory, like in 2025. I want to I'm in the process of building a new factory, and I want to simulate what's going to happen when everything falls into place, right? I have the conveyor belts, and I want to essentially see how fast I can paint my pieces and build my engine parts and whatnot. So I have a world simulation that does just that. How about I try to feed the simulation with data that actually comes from real devices for which I have a twin in my environment, and I can do just that using the Python API that Blender exposes. And in literally just a few lines, I can query the Azure Digital Twins graph to, and I want to find, where is my query? Yeah, there it is. Every few seconds, I can be like, hey, digital twins, I need to know what is the robot arm that is currently, and it might change, right? It might be highly dynamic. Currently, what is the robot arm that is controlling assembly line? Assembly line 0001. That's the query I want to write. It's not a query where I'm like, hey, digital twins, give me dofbot 001. No, it's way more dynamic, right? I think you get the idea. And so that particular script, as soon as I start running it, it will start getting data from the digital twins graph in real time. And as soon as it starts updating, I think you can already see that the position of the arm in the simulation is the same as the one in the real life. And if I move it, it should move in real time, right? And to the point, actually, where if you look at this view right here on the in the upper right corner, the view we see is what the camera that the robot arm has, what the camera would see. And I think that one I found actually pretty interesting, because I could very well script my 3D environment so that I take snapshots of what the simulated camera sees, so that I capture the data and potentially use the data to train a computer vision model. Right? I want to train the model to detect parts that may have some defects. I could do just that, right? And so that's I guess that's for the connected aspect of the solution. And now, real quick, sort of the closing the loop. And it might not be like maybe the most impressive or the most important part of the demo is now over, but there is one last interesting bit, I think, which is leveraging the fact that micro-ROS and ROS make it super easy to add new nodes and that are very much decoupled from one another. And one thing I did really, really quick, and to show interoperability as well, is using another MCU, this time a Cortex M4F, slightly more powerful in terms of memory and flash, but still really, really small. And this one has an LCD display. So on that one, I used Azure RTOS ThreadX for the operating system, NetX still for the networking stack for doing UDP, and it actually doesn't show in the text here, but it should. And then GUIX for the graphical user interface. And this guy is subscribing to some data coming from the local micro-ROS environment, but is also integrated with the digital twins graph. And what essentially what that means and what that enables is, and I can maybe stop sharing real quick so that you can see me full screen. You can see the Wayo terminal at the back here, and maybe you couldn't see it earlier, but it's in real time. It's actually showing the position of the different servo angles. Although right now it looks like it might not be, but not only is it showing the position of the servo motors, but it's also showing information that is something that we couldn't get locally, right? What is the part that the device is currently that the arm is currently in the process of painting? This is something that this is context that comes from the digital twins environment, right? So that's I think that's actually pretty interesting to add that to the mix. And I think that's pretty much what I had as a demo. I'm gonna reshare my screen real quick to wrap things up as soon as I find up the. There we go. No, opening up to discussion, I guess now. But to wrap things up, it might not be news for many of you, but I think, the technology to support robotics on constrained nodes is there for sure, and including actually the part where we start thinking about IoT scenarios or metaverse. And I think, and I hope that the demo I showed and that part about potentially training a computer vision model using the simulation, things like that, I hope that convinces you that it's way more than just a buzzword. And I hope we can get to work more together on improving the developer experience for making it like super seamless to build micro-ROS applications. And I've included my contact information as well. I will make sure that it's in the Google Docs too. But I hope, pretty excited about where this will be going, basically. So that's what I had, and I might not have run over time too much.
Thank you. Thank you very much. We hope to have you again here very soon. Well, now we have a couple of minutes for any comment or any question from the audience or something you want to add.
And I should add that I had promised Maria and Pablo that the code for the demo would be open source by the time we do this meeting today. It's not yet. There's no reason it's not, except the fact that I just need to find a time to make sure that everything is available on GitHub. But yeah, there's no secret whatsoever there. Quite the opposite. Like I really would love for anyone to replicate the demo setup, including the Blender-based simulation, potentially playing with other kind of backends. It doesn't have to be Azure IoT. I think showing interoperability there is super important. But yeah, it'll come. And I will make sure to update you as soon as the code is available.
Just mention that we have both the Azure RTOS component for micro-ROS, where you can integrate micro-ROS in the Azure RTOS build system, and also you have available a component in the Renesas micro-ROS IDE, where you can use ThreadX and NetX and all the stack layers that they have in the Renesas hardware.
Yeah, thanks a lot for this very impressive demo. I have a short question regarding the implementation. So on the slide where you showed the communication to the in the use case, it looks like you're not using the micro-ROS agent. So the communication goes directly to the cloud. How is that implemented?
That is correct. That might not be. Either might not be a good idea, or at least that's not the only way it could work. Yeah, the STM dev kit, this particular dev kit, it has a Wi-Fi chip, and it has enough room so that we can both connect to the local network, to the agent, the micro-ROS agent that's running on my desktop PC in my home, if you will, but at the same time also establish a TCP/IP based connection with a public cloud. Now, in real life, on a real factory floor, it might very well be that the MCU doesn't, although the MCU might have access to a UDP stack to talk to the micro-ROS agent over UDP, it might not have access to the public internet. So in that case, either there will be another node somewhere in the system that's going to act as the proxy, if you will, is going to subscribe to lots of telemetry, lots of topics, and will be forwarding those topics to the public internet. Or or maybe the MCU will talk to some kind of local gateway over, like using MQTT or another form of protocol and that gateway will be in charge of forwarding the data to the public server. But yeah, does that make sense? Does that answer the question?
Yeah, sort of. I just wanted to understand for you the benefit of using the micro-ROS.
As opposed to?
Yeah, I mean, typically in micro-ROS you have the agent and communicating to the ROS2 world, and now you're just using the micro-ROS client on the microcontroller.
Yeah,
right?
But it's like maybe I think I get the question and the idea. I guess for the sake of the demo, the use case is pretty dumb, if you will, in that there is a ROS2 node on my PC that is basically just publishing servo positions, and then the micro-ROS client on the MCU is just subscribing to this data, and that's the only form of communication that's involved. But there's nothing that prevents. I mean, it would be useful to have more nodes, and in which case, like the micro-ROS client on the MCU, we actually need it, right? Like it's the ARM is still being controlled by means of ROS. It's not being controlled by means of the IoT platform, right? It's IoT comes, like in this particular scenario, comes almost as an afterthought, but an afterthought that is super easy to add. It's like you build your micro-ROS based solution, and then once you're happy with what your MCU is doing and the way your robot behaves, at any point in time, you can start exposing the data that you think could be useful to be exposed to the IoT platform. You can really easily expose it and start publishing it.
Okay. Mm-hmm. Thanks.
Okay, thank you. Thank you very much. We should move on now with Dominik from Husarion. He is having 2 topics today. So Dominik, whenever you're ready, please.
Yes, so thank you, Maria, for the introduction. Can you hear me well, the first question?
Yes.
Okay, cool. So I'm also the first time here and the first time presenting here, but I hope not the only one. So today I have got 2 topics to cover. The first one is about connecting ESP32 powered microcontrollers running micro-ROS over the internet with robots that could be in totally different networks, and everything done peer-to-peer. So maybe I will share my screen right now. Okay, so today I have published the full article about the topic that I am going to present right now. So I will send you the link, that article. And basically, let's go to the architecture chart. Discuss the use case in details. So basically, imagine that you have ESP32 Wi-Fi microcontroller that runs micro-ROS. My example is really basic because the let's say idea is to show possibilities and how to communicate, devices operating in totally different LAN networks. But this is a very, let's say, basic demo when you have a Toggle node running on the ESP32 microcontroller. And on the micro-ROS agent side, you have running on the laptop, you have got listener node. But you can imagine that this system could be much more complex when you have not only one ESP32 microcontroller, but the whole, let's say, network, IoT network of such devices. Imagine, let's say, motion sensors located in different parts of the building and connected to a single node, to a single robot device server, doesn't matter, that is running micro-ROS, and then a micro-ROS agent, and then from the level of this micro-ROS agent, the information could be provided from those motion sensors to as many robots as you want. And the most important aspect, let's say, for our side, what we have added to the whole system is the VPN connection between IoT devices and between micro-ROS agent. So Husarnet, our company, is providing a peer-to-peer VPN network that is as lightweight as it works even on ESP32 microcontroller. However, we have also client version for Linux, for Windows, and we're going to release Android and macOS versions very soon. But basically, what Husarnet allows you is to connect those devices not only over the internet, but connect those devices peer-to-peer over the internet. So basically, Husarnet helps your devices to find each other over the internet, even if they don't have a public IP address, if they are behind NAT or firewall, it doesn't matter. Husarnet allows those devices to connect to each other over the internet and acts as they have a public IP. But this public IP is not really public IP, but let's say virtual public IP within Husarnet overlay network. And this IP provided by Husarnet is IPv6. So thanks to that, you can easily share your network with other users, with other robotics fleets, just with one click. Okay, so here is my demo that I will present here. I have got a full source code provided. It's open source. I will present you everything. I will make a live demo showing you how to connect this ESP32 board together with 3 containers running on my laptop. So the first container is micro-ROS agent. The second one is a Husarnet container that provides a peer-to-peer connectivity for this micro-ROS agent node. And the third one is listener node. So from demo nodes is CPP. So the very, very basic, let's say, ROS node. So let's go to this open source project. And I have marked that project as a template. That means you can easily copy that project to your own repository. So I will also share your link to this repo. Okay, and let's use this template. I will name my project micro-ROS demo. Okay, the project is ready to be cloned. So let's copy the link. And let's open it in Visual Studio Code. So my project is based on a Platform.io framework. And what Platform.io does is installing all project dependencies automatically just after I clone my repo and open it in Visual Studio Code. That means all required libraries and things like that to run this demo are already here. So the first step to run the demo is to so maybe I will show you the source code, what is how it looks like. So everything is this very simple demo. So 170 lines in total. So micro-ROS code starts here. So we create the node, create the publisher to the chatter topic, and run it basically. And there is a new let's say a transport provided by us, and it is available on the fork of micro-ROS on my repo. And thanks to this dedicated transport, you can initialize this transport only by providing 2 parameters. So the first one is micro-ROS agent hostname. This hostname is something that you can use alternatively to the IPv6 Husarnet address. So all devices also has host names, thanks to which you can access them easily without remembering this long IPv6 address and the port to which on which micro-ROS agent works. So the first step is to provide Wi-Fi and Husarnet credentials, allowing you to connect ESP32 board to your Wi-Fi network and then to the Husarnet network. So for that, I have created a credential files template. So let's rename it to just credentials.h. And let's provide Wi-Fi credentials at first. So here is my my local network at my home, and the second step is providing a unique Husarnet join code, allowing you to add a specific device to the same Husarnet VPN network. So to do that, I need to go to the Husarnet dashboard. So app.husarnet.com, or maybe from the beginning, dashboard, right? I'm here. And then I have created the micro-ROS ESP32 network. And right now I will add devices to that network. And after adding devices to that network, those devices see each other like they were in the same LAN network. Even if they are in totally different networks, even if they are connected over the internet and are on the different continents. So I have just copied the join code, allowing you to connect those devices. Okay, and let's place this join code here. Okay, and we need also to connect micro-ROS agent to the same Husarnet network. And the micro-ROS agent code, the part running on the laptop is described in this Docker Compose YAML file. And this Docker Compose YAML file also requires you to provide the end file. And in this end file, you need to provide the join code. So I will also rename this file from env.template to just env. Okay, and let's save it. Everything is saved. Okay, so to start the micro-ROS demo, you need to run a micro-ROS agent at first. So let's go to the demo folder. And let's start all those 3 containers. As you can see, agent is already working. And agent and Husarnet container is providing a VPN connection. As you can see, the Husarnet IPv6 address is like that. But alternatively to Husarnet IPv6 address, we can use the host name that we provided here. So the host name of this device is simply micro-ROS agent. Okay, so the next step is to program our ESP32 board. So this is my basic dev board with ESP32 chip. So I will just click a platform IO upload button, and that's the only step I need to do. Okay, the project is building. Whoa, sorry. Probably I have moved the USB connector and the connection was broken. So once more, I will flash the board. Okay. Okay, so let's open serial monitor. Okay. So so my ESP32 board has just connected to my Wi-Fi router. Has also connected to the Husarnet network. As you can see, it is publishing hello world messages. And let's go back to our Docker Compose stack. And as you can see on the Docker Compose end, I am receiving the same messages sent by ESP32 to the chatter topic. And I'm receiving them on the listener end. Okay, and basically that's all. As you can see, bringing it to life is quite simple. It's quite straightforward. So the whole source code is open source and provided on my GitHub. Yeah, and also more details about what is happening here, and things like that. You can read more in my article that I provided link in the comments.
Thank you. I have included the link of the repo also and the article in meeting notes of the embedded working group.
Perfect. Thank you. Okay, so before jumping to the next presentation, maybe if you have any questions, let's do it right now.
Just mention that we are going to merge soon these modifications and this transport that Dominik have developed in the mainline branches of micro-ROS in micro-ROS for Arduino.
Maria, you are muted.
We should jump to the next topic in the interest of time.
Okay. So my next topic is, let's say, quite similar. So I will also present an open source demo showing you how to connect microcontroller with micro-ROS agent, but this time not over internet, not over Wi-Fi, but over Ethernet port. And in the same time, I would like to introduce you to the new robot that we will release in March. And this new robot is the product of our second company, because Husarnet and Husarion are two separate companies. The first one is providing a peer-to-peer VPN for robotic use cases for ROS and for ROS2. It works with those systems out of the box and has, let's say, interesting features for that. But our second company is a manufacturer of autonomous mobile robots. It's called Husarnet, and I would like to introduce you to our newest product that we will release in 2 months. Okay, I'm presenting my screen already. So, okay, here is how our robots looks like. And here is how it looks like in real. And of course, the firmware for this robot will be based on micro-ROS, and it will be open source. It is still work in progress. However, I will share you a link to the template on which we have based the firmware for the robot. So the template is, let's say, the combination of different libraries and technologies combined together into a repository that you can just use as a template, use as a boilerplate for your own product or for your own project. And basically, our robot is based on STM32 microcontroller. And this open source demo shows you how to connect micro-ROS agent working on your laptop together with the STM32 board over the Ethernet. And as in the example that I presented before, the demo is the same. So the toggle and listener demo, but this time not on ESP32 board, but on STM32 F4. And that's also platform IO based. So you don't need to worry about any project dependencies. Everything is installed automatically just after you open this project in the Visual Studio Code with a Platform IO extension. Okay, so let's go to the block diagram of the robot. So basically, robot contains a digital board, and this digital board contains Ethernet switch. And to this Ethernet switch, both STM32F4 is connected and a single board computer, but also Ethernet socket is available outside of the chassis of the robot. So you can easily connect your own laptop to check something in the system and so on. And when it comes to single board computer, we let's say made this platform as universal as possible. So the only interface required between a single board computer and the digital board is Ethernet. So you can use ROSbot XL with any single board computer provided on the market. So like Intel NUC, like NVIDIA Jetson, like Raspberry Pi 4. So this platform is quite universal. It has quite advanced power board along with embedded Lion charger. You charge that robot by using USB-C port. So you can use just a charger from your mobile phone. And also it integrates four DC motors with encoders, and also a nice pixel LED strip allowing you to make effects like that. Okay. So I will maybe stop presenting and show you how the prototype, the pre-production prototype of the robot looks like. It's about 50%. Let's say each dimension is about 50% larger than in the regular ROSbot. That is one of our most popular products. As you can see on the real panel, you have got access to Ethernet, connected to this Ethernet switch, HDMI, 2 USB ports, some buttons, some LEDs, and of course, a connector for USB-C charger. And on top of the robot, you can mount anything you want, LiDAR, robotic arms, and also our power board provides enough power for open manipulator robotic arm, for example. So that's let's say great prototyping platform and a great research platform for say many indoor ROS use cases. So stay tuned. In March we will release both this robot and open source code for this robot, because this platform will be totally open source. But right now, remember about this link to the project template based on STM32 that I have provided, and from my end, that's all.
Okay, thank you very much, Dominik. This was really insightful. Yeah, it's very nice to see micro-ROS in ready-to-market platforms such as yours that will be in the market in the first Q. Well, last week there was a big launch also. We're very happy about it. Now, in the interest of time, Pablo, you will choose a couple of topics.
Yeah, just a couple of minutes. What we have been doing during this month. We have been integrating a new Renesas board, RI62, that is a motor controller board that have CAN-FD transport for micros. We are testing it, and we are going to merge the release in the main branches really soon. This is the second official releases board that we support in micros. It includes the new transport, the CAN-FD transport, and both the client and the agent now are able to speak XCDDS middleware on top of this new hardware transport. Also, we have a new community-supported MCU, the ESP32S3, that have, according to its web page, AI acceleration support. It's available on the micro-ROS for ESP IDF component already merged. And finally, I want to mention that our partners at Capra have just released their first mobile-based robot that includes inside of it a custom board based on STM32 that runs micro-ROS. We have been working with them the last 6 months, and we have improved a lot of things of micro-ROS thanks to them. Mostly things regarding to multi-threading and agent resources optimization, a lot of things, and now we can see that we have the first commercial robot that uses micro-ROS in its core. You could have a release note here, a press release here. Maybe in another embedded working group they can present this new robot to us. I know that Bartolome and Anastasia are here. So that's all on my side.
Great. So we have reached the top of the hour. The recording of this meeting will be online at the end of this week, and it will also be added to the meeting notes document. Okay, well, I want to thank everyone for attending, especially the speakers. Really, really great embedded working group. We will be back next month in February with more interesting use cases and topics. So thanks everyone, and have a good rest of the day. Thank you.